Yes.
All right. So okay, works. Any other questions? All right, so we are down to our final lecture. Today I want to talk about, some of the advanced topics and review the things that's going to be in your quiz too, as well as generally just a full discussion about, various things that we did in this course, kind of like, to summarize all the things that we said. So this is kind of like the agenda. So last time we talked about synchronization and in general memory consistency problem. Make sure that you do your homework 6. It's going to be due tomorrow, and your quiz will be also very relevant to that homework and the homework before that. I'll talk about your quiz a little bit. So we talked about what was the problem of memory consistency, why we have memory consistency problem. And then we start talking about, how to fix it. And in order to fix it, we needed to first to understand what is the memory model. We talked about sequential consistency as the strongest one that doesn't allow any reordering. Then we talked about TSO, which is basically the ones that, widely used and very popular and doesn't allow you to reorder writes, but it allows you to, reorder reads before writes. Excuse me. And then we talked about, release consistency or generally weaker models, which allows you to do any reordering that you want, and under some circumstances, stop that reordering. We mainly talked about release consistency as the ones that, use, mutexes and locks in order to, make sure that the reordering happens in the way that we expect. Generally, the idea here is that, we should allow the hardware to reorder things as much as it can. And we should write our programs using the APIs or the tools that it provides to us in order to allow us to write the program in a correct and predictive way. Okay, so that's kind of the general methodology when it comes to multi-threaded programming. Okay, so the burden is mainly on the programmer as opposed to most of the things that we learned so far, that the programmer just writes the program as the way they want, and the hardware is kind of the ones that keep track of things in the background and so on. For the multi-threaded programming, it's kind of the opposite. So the hardware provides the primitives, but it's on the software developer to kind of write the program in the correct way. And that's why generally writing programs, multi-threaded program for software is quite challenging. So there requires lots of expertise and so on. If some of you guys in job market will probably know that those type of jobs, and actually it's much more higher pay than regular software developers, just because of this complexities. We talked about various solutions, including fences, barriers, or in generally semaphores. We talked about locks and how do we use the locks and how do we implement locks, and that was kind of it for our memory consistency problem. Okay, any questions about memory consistency or your homework? Okay, so I want to finish this story that we started in the very first lecture. If you remember, we said that we generally started kind of like, our modern processors start somewhere in the 70s. And then, and afterwards, we kind of grow. The reasons for that growth was two main things. One was generally we managed to, build and implement better hardware. This is mainly thanks to advancements in technology, in the CMOS technology in particular, and then moving into a smaller generation and smaller generations. And that gave us kind of like, this period of, we get what we call the Moore's law kind of like, improvement. Then the speed is kind of like, doubled in what we call the golden age of the computer architecture, which here was all these things that we talked about in this course about pipelining and out of order execution and branch prediction and so on and so forth. So not only we benefited from the advancement in hardware design, we also benefited from this new ideas that we introduced in this class. And we said that it's kind of slowed down after we hit the power wall, so we couldn't really add more and more these new techniques to the hardware. What we kind of like help us to move forward was the multi-core design. So we added more and more cores, and these cores help us to improve the speed of multi-threaded programs. We needed to fix the consistency and coherency problems, but once we fix that, we kind of like get this performance out of our systems. And then things start slowing down, and we are kind of like in this era that really we're not getting much more speed up as previous years and previous eras. This is because of all these limitations that we are hitting, right? So we cannot really add more cores because cannot really power all these cores together. There's not much parallelization left. So for example, if you have already like 80 cores or some large number of cores, there's so much that you can parallelize because you're going to hit the Amdahl's law at some point, because there will be a serialization point in your program that no matter how many cores you have, that part's not going to be faster, right? So we kind of look at this point in history that our system doesn't really get much more faster. Okay, so the question is this, like, where are we going now? What does the future looks like? And when I'm talking about future, I'm talking about the recent years. So it's not just things that haven't happened yet. Some of these things already happened, and most of these companies are actually using these ideas. Okay, so it's not it. We as I told you multiple times during this course, we always hit some wall and then we manage to jump over it, right? And the hope is that we're going to continue doing that. And at least all the evidence points that we will manage to make this systems faster and faster. So there are three things that I want to talk about. What we call Moore. So basically what it says is that really Moore's law hasn't been ended. There are chances that we can increase this. Then there's more than Moore, which mainly says about we are adding other things to our processors. And then the final thing is kind of like we can actually move forward from CMOS technology, and maybe we can start thinking about other technologies, including quantum computing and so on and so forth. So I'm going to talk about these three. Let's talk about the first one. So more Moores means that this is mostly thinking about short-term solutions at the device level. There are new technologies such as FinFET, or using better materials, or using new technologies such as 3D memory and so on, that will help us to kind of like continue the integration and reducing the transistor size, right? So we go to 3 nanometers or maybe 1 nanometer, who knows? Okay. There's also what we do at the architecture level is about customized computing units, domain-specific computation. So what we have done so far is mainly saying that, we have a CPU that has this instruction set architecture, and we are given a program and we're going to run this. But since new applications coming in every day, we started at some point in history talking about, let's actually have additional kind of like customized architectures that's kind of work hand in hand with the processors. In this lecture, I'm going to talk about GPUs and accelerators a little bit. So the idea would be that we don't need to do everything in the CPU. The CPU can collect this and then can start distributing it into more advanced and specialized part of the hardware, and we call those accelerators because they are designed to do a specific job faster. So it's not accelerating the entire computation, but maybe accelerating, for example, matrix multiplication, maybe accelerating your or zipping or unzipping of your file, maybe accelerating your encoding or decoding of your video files, and so on and so forth. Okay, so the idea of the customized units is okay, let's add these things that are really, really good at one specific job rather than really good at all the instructions. And then another thing that, these days are being used is what we call processing memory or computing memory, or PIM. What PIM does, processing in memory does, is that, we have this problem of we have a memory and we have a computation. And in order to read things, we need to go to the memory and bring things to the processor, right? And this, as you have seen, there's lots of delays. For example, if you go to the DRAM and come back, we're talking about hundreds and hundreds of milliseconds. So the idea of computing memory is actually, if you have technologies such as 3D memory and so on, what we can do is that if this is our memory and this is our processor, maybe we can add a tiny bit of processing on top of this, this memory, okay? So think about this as a 3D process, and this processing would be on top or at the bottom of on my memory. And with the technology, I can actually have a connection between these two. And this way, this connection between the processor and the memory would be much, much, much more faster than this process here. The challenge is that I cannot have as strong as, sophisticated processor as what I would have here, mainly because thermal issues, technology issues, and so on. But maybe some minimal things can be done here. So maybe like addition, right? Or simple multiplication. And there will be lots of applications that could benefit from this. For example, think about matrix multiplication, right? So matrix multiplication is all it needs is just get two values, just multiply them and add them together and have some partial sums and just add the partial sums together, right? So we really don't need to be able to support all the instructions, but maybe some tiny instructions, if we can implement it in this tiny processor here, then we don't need to transfer back and forth data from memory to the processor. We can do things in memory itself. And that's just makes it much, much more faster for certain number of applications. Okay, so processing memory and generally domain-specific accelerators help us to boost our performance, and most of these improvement in this era is actually coming from this technologies, really, because at this point we kind of we are at best in terms of multi-core systems. What really happens at this era of 2010 so forth, so on, is mainly this domain-specific accelerators. And I'm going to talk a little bit about GPUs and accelerators later on in this lecture. And then the final thing is at the system level, we also add more things. So all this notion of Internet of Things, cloud and IoT devices, like collaborative environments, embedded systems, and all those things. These are new paradigms that we added to our system in order to make our system faster, right? So it's not just about having better hardware or having more better architecture, but it's also about system level innovations that we made in the past few years, mainly to increase the quality of service and mainly improve our quality of life, right? So we added things like watch, we added smart, sensors in our home. We did lots of smart applications in our environments, and all of these are thanks to this new way of thinking that, okay, we can add hardware and computation to many things that we do manually or we do mechanically in our work, right? Autonomous driving, for example, is another one that's hopefully will happen very soon. So things that we assume that we should do manually now, it's going to be completely automatic and controlled by computers, right? So these are all under the category of what we call more. It basically says that, we're going to add more computations wherever we can, and we're going to specialize it, and we're going to add more technology. We're going to throw technology at the problem, and hopefully it will improve. It won't completely solve the problem. At some point, we're going to hit the limit, but there is still a lot of available area of exploration for these kind of technologies. All right. Any questions about more? The second strategy is what we call more than more. So the idea is that the technology that we use in order to create a chip could be combined with all these other things that we do in our system. So for example, this is the image that I'm showing you, and this is actually not something new. It's something that we've been using for a long time. And this is mainly thanks to integration technology and packaging technologies that also gets really mature these days. So we started with multi-chip modules and integrated systems. These days we are able to have what we call a 2.5D ICs, which essentially instead of like having one chip and the other chips kind of like on the other part of the PCB and having lots of delays between them, we put all of them in one part of silicon, so the connection between these chips is very, very fast. We also started looking at the 3D ICs, so it's not just one core. The cores would be like on top of each other's. And what we have right now is we are basically having what we call a chiplet systems that we will have lots of these chips. Some of them will be 3D, some of them would be 2D, and then all of them will be integrated into one part of silicon. And the significance of this is that the connection, the delay between different units would be much more smaller than what we normally get. Okay, and then we can add our sensors to it. We can add anything we want into the same piece of silicon, and that means that our connections, our bottleneck, which was, for example, from memory to the processor and so on, is kind of like reduced. Okay, and this is actually what is happening with this new generation of Apple SoCs, right? So they put everything into one substrate, and that's why the memory is much more faster than many systems that we have right now, because they managed to implement this into an integrated fashion of a system. Okay, I'm not going to go through the details of this because this is more of like more at the device level, but the idea of that we can add more things is what is going on right now. If you're interested, check out, for example, chiplet technology and see what is going on out there. So most of these companies, including Intel and AMD these days, they're using chiplet-based systems rather than the normal SoC systems. Okay. And then finally, there are a whole bunch of other ideas and technologies in order to make our computer, revolutionize the way that we are building computers and make our computers significantly faster. Quantum computing, you probably have heard about. There's other options as well, including like photonics and optical computing, neuromorphic computing, hyperdimensional computing, and so on and so forth. The idea of in most of these systems is just go beyond CMOS technology and try to use other technologies in order to make computers faster, right? One thing to keep in mind is that when we are talking about like things like quantum computing, doesn't mean necessarily that quantum computing going to replace your CPU design or your system. Quantum computing going to be added to your system. So there will be a class of problems that quantum computing would be great for, and it's going to increase your speed. But most likely the CPU design and all of these general purpose systems and ISA and so on will stay. The way it will work is that you write a program, and some part of your program will be accelerated by the quantum computing applications. Okay, so these are more for now, we really don't have any of these at the consumer level. It's more of researchy ideas that people are keep thinking about. Quantum computers, for example, right now is around 100 qubits. So we are kind of like for quantum computers, we are somewhere around like where we were for general processors that are like 60s or 70s. So we are at that point. But soon, as I told you that soon we hopefully will be able to go past the technology roadblocks and then have computers that's really fast. Okay. So to just recap, we managed to increase the performance at rate of 2x every 24 months for this past 40-50 years. We use lots of microarchitectural tricks that I extensively talk about in this course, and that helps us to improve this even further by a factor of 25, in fact. We hit the power wall, and then we added multi-core systems. There were some challenges with multi-core systems, but correct implementation of hardware and software will help us to fix that. And we are kind of like at that point that those tricks are kind of ending, and we need to look for new techniques. The three ones that I described is more than more, and beyond CMOS. And these are basically what we are right now and what we're going into future. And important things in all of this is that, and as I told you at the beginning of this class, is that regardless of whether you're going to work as a hardware designer or computer architecture designer, operating system designer, or just pure software, backend developer or web developer and so on, you need to understand how your system works, essentially how your hardware works, because we no longer can get the performance we want if we just say that, oh, hardware is going to take care of it or software going to take care of it. We need what we call a cross-stack approaches, that the hardware people should understand how the software works, and the software people should understand how the hardware works. Because we kind of like did all the tricks that we knew already and used them all. From now on, what we really need is kind of like, what we call a co-design or cross-stack applications, right? We need to understand how our cache works so that we can design better software. Right? So we need to understand how our coherency works in order to design a better system. So we really need to have a better understanding of this hardware software, the entire system, in order to be able to get the performance out of this system. Okay, things have get complicated, and we need to we need to understand this complication, and we need to have a better view of all the things. 20 years before, maybe we didn't need that, but these days we definitely need that. Okay. All right. Any questions about these things that I just said? All right. So let me also talk quickly about GPUs and accelerators, and then I'm going to kind of finish with new things. So we talked mainly in this course about general purpose CPU systems, right? And we talked about the memory subsystem as kind of like helping the CPU. But there's also these days, main part of any computers is GPU. So you won't buy computers that doesn't have GPUs. And you might ask why we need GPUs. I mean, in the past, GPUs were mainly started to be used for graphical purposes, for rendering and doing those kind of things. But these days, GPUs are extensively used for any sort of applications. And the reason that we need GPUs is what we call data level parallelism, right? So if you remember, we had instruction level parallelism, ILP, and there we said that we basically have superscalars, and we have multi-level, multi-lanes in our systems, and then we have things like simultaneous multi-threading and so on. And that was mainly the ILP part of our system. Then we talked about thread level parallelism, or TLP, and we said that we add more cores, we create multiple threads, and these threads are running on multiple cores at the same time, and that would be our thread level parallelism. But then there's also data level parallelism, or DLP. And what DLP says is that, there will be scenarios where you have a large amount of data. Let's think about it as a vector. And all we need to do is basically just do one instruction at a time on this entire data. So if you think about it now, if I have, for example, if I want to add two large vectors together in my general CPU system, we have to create a for loop, and then we have to add them 2 by 2, right? So it's kind of like, create a for loop, add the first two, then add the second, add the third, and so on and so forth. So each one is one instruction, and each instruction kind of runs one at a time, right? But if we could have maybe added, instead of like adding 32 bits by 32 bits, we could have added 1,204 bits to 1,204 bits. The same addition happens, but it's just a larger amount of data. Then we could have had, much more faster systems, right? So same instruction, but multiple data, or what we call a SIMD system. It's basically when we are saying that, we're going to have data level parallelism. The instruction is the same, all the pipeline stages, everything is the same. It's just we want to view this in larger size for the data. Okay, and this is where GPU can comes into the play. So GPU can help us with this massive data level parallelism. And the main use case, that the main reason that GPU becomes so popular these days is because of the AI or machine learning applications. So basically, machine learning has become the killer app for these GPU systems, because machine learning itself is really useful for lots of new problems that we haven't been able to fix before. Things like computer vision, classification, natural language processing, voice recognition, and all those things. And in order to implement this machine learning applications, we usually need to deal with lots of large data and lots of matrix multiplication and matrix analysis. And GPU exactly gives us what we want, because it's allow us to do data level parallelism in a very efficient manner. Okay, so that's kind of like the reason that GPU these days becoming so much more popular. And the idea that we are using GPU these days is what we call GPU, or in other words, general purpose GPUs. In the past, GPUs are, as I said, mainly was used for specific applications, kind of hard-coded in hardware. For example, for rendering, for displaying things, and so on. But nowadays, if you have any applications that you write in a specific language, which typically is CUDA, if you write your program in CUDA, then you can upload it to the GPU, and GPU can run it for you. So it doesn't need to be specific application. It could be any applications that runs using that specific language. And the good thing about this, as I said, is that this could be used for many different things that can benefit from data level parallelism. As I said, machine learning is the big one. If you're into cryptocurrency, for example, mining is another big, killer app for GPU systems, because for mining, you also need to check the same data over and over, right? So all things that kind of basically require same instruction, but large amount of data, a stream of data, could benefit from data level parallelism, and generally could benefit from GPUs. And the way it works is that, as I told you, GPU is not going to replace CPUs, but the model would be this, that, we still have our memory, we're going to have our CPU, and still we're going to have our PC, and the PC going to go through the memory and bring instruction. Then there will be a group of instruction, which we usually call kernel. Think about it as one set of program or part of a program, one function within a program. That this part of the instruction, which we call kernel, instead of like the CPU gonna read this, and instead of running it, it's gonna offload it into the GPU. And GPU gonna take this kernel and then gonna execute this kernel using the model that it has, and it's gonna send back the results to the CPU. So the results going to be sent back, and then the CPU can interact with the memory to store the results, and so on and so forth, right? So still the CPU is the orchestrator, the controller in the system. But the way it works is that, there will be part of the program which will be defined by the user. And these kernels will be offloaded to the GPU. The GPU will run those. Doesn't need the involvement of CPU anymore. Can just run these kernels independently, get the results, send back the results, and the CPU just continue whatever it does. CPU, when offload this computation to the GPU, can just continue running other things. So the CPU doesn't necessarily need to stall or stop. You can just offload and then move on. Okay, and think about this, for example, as a matrix multiplication. So think about this as you write a program that reads some input, it wants to do the matrix multiplication. Instead of just writing a for loop that goes through every element and multiply it and so on, the way it works is that as soon as it recognizes this using the programming language and so on that we're now going to talk about, it's going to upload it to the GPU. GPU going to run this, send back the final results of this matrix multiplication, and then the CPU will move on to the next part of the program. Okay, and as I told you, this is GPU, which means that these days we are using GPU as general purpose. So any applications can be uploaded as long as you follow the format of how you should write a CUDA program. If you write it correctly, the operating system will recognize it. It it's going to upload it to the GPU and then you can use it. So it's not just, it's hard coded or anything. You can run any program that you want. You can even write the programs that normally being used in a CPU and upload it to a GPU, if you will. It's just more complicated and sometimes less efficient. Typically, the applications will benefit a lot from GPUs is those applications that has lots of data and lots of DLP opportunities. All right? Any questions? So to give you just some perspective of how CPU and GPU compare, if you remember, we kind of like had some form of like, the simplified version of a CPU was some controller, some bunch of, functional units and FUs. And then there was like, memory hierarchy, which was the cache, right? Sorry. Which was the, the cache system and the DRAM system, right? So control unit was, all the, fetch, decode, rename, all those things. So these were all implemented here. Then this part was basically our functional units. And then we get the results back into our controller and then we interact with the cache and with our main memory, right? So that was the model that we discussed extensively in this course. The GPU one is basically still have some controller, it still have some cache and DRAM, but the majority of the GPU is basically functional units. Okay, the overwhelming majority of any GPU system is lots and lots of functional units. And if you remember that just told you that, the reason that we need GPUs is because we want to do the same thing over a large amount of data, right? So we're basically saying that, okay, instead of having 3 functional units, let's have thousands of functional units. And all we need to do is saying that, okay, let's say we have a reservation station that says, add these 2 numbers. I'm going to add these 2 numbers into these many functional units, and each one going to use a separate register. Okay, so if I have a really, really big register file, what I can do is that saying that, okay, instead of adding x1, x2, I'll issue one instruction that says add x1, x2, then the other one would be x3, x4, all the way to x1000 to 1001, right? So if I have a large register file and many functional units, what I can do is that I can kind of like scale this amount of, adding that I can or multiplication that I can to a very, very large number of things, okay? So the general idea of GPU is this, that I need lots of functional units because I need a few instructions, but lots of same instruction over the large amount of data, okay? So the hierarchy of the GPU, so this is mainly the terminology that NVIDIA is using, and it's kind of, extensively used in most systems. So we have 3 things in a GPU system. We have threads, which basically threads, think about it as a process that we had in CPU. So a thread has what's called a thread ID. It has a program counter similar to a processor that we have. It has registers. It has per thread memory, okay, private memory, and then it produces the results. Then group of these threads becomes what we call a thread block, okay? Think about thread block as what we had in a multi-core system. A group of threads together shared a level 2 cache, okay? And then we're gonna combination of these thread blocks create what we call a grid. And the grid is mainly a program, okay? So one kernel that we want to send is typically one grid. In some rare cases, there might be multiple grids for one kernel, okay? So we have threads, thread blocks, and grid, which is a combination of thread blocks, okay? And then typically this grids shared a global memory, and think about this as our DRAM basically in our CPU. So we have private local memories, we have shared per block memories, and we have a global memory, okay, which is kind of like shared among all the grids and so on and so forth, okay? So kind of like to give you one the programmer level or execution model, the system gonna have, as I said, this whole thing is called a grid. Within grid, we're going to have blocks. Each block going to have a number. And within each block, we're going to have threads. So for example, we can have if our block dimension is 256, it means that there are going to be 256 threads within this block. There will be, for example, I don't know, the number of blocks depends on the size of the inputs and so on. So how do we pick these numbers? These numbers are being picked based on the problem that you're trying to solve, okay? So for example, if you're trying to add thousands of numbers to thousands of numbers, most likely you need 1,000 threads, okay? So how do you divide it to blocks and into threads? That's mainly depends on the algorithm that you're going to use and the way that, you know, this parallel programming works and so on. We're not going to go through that. It requires a separate course on how do you write CUDA programs and so on. But think about that, you know, generally what we want at the smallest level is threads, and threads is really that, you know, simple, you know, instruction set that you need to execute, and then you combine it into blocks and into the grids, okay? So to give you a little bit of hardware terminology for GPUs, so one GPU is runs one grid at a time or multiple grids at a time. Each of these grids, as I told you, there are blocks within each grid. Each of these blocks usually assigned to what we call a stream processor or a SEM. So each GPU typically has somewhere between 16 or 32 SMs. Okay, SM, think about it as just one big core. Okay, within each SM, then there are multiple smaller cores in GPUs. Okay, so stream multiprocessor has you know, cores within it, and then within each SM, we typically have multiple number of cores. Typically, we have 32 cores per SM, and we call that a warp. Okay, so a warp is the number of cores within an SM that, you know, the system, the scheduler use in order to run threads at the same time. So the GPU scheduler typically runs things at warp scale, which typically 32, which means that each SM runs 32 threads at the same time. So we have 32 functional units in some sense that can help us to run 32 threads at the same time. And if you have multiple of these SMs, then you have 32 times the number of SMs parallel threads that we can run at the same time. Okay. To give you a little bit better idea of what's going on, this is the macro architecture of 16 SM Fermi GPU. So Fermi is one of the newest NVIDIA architectures, not the newest. I think this is like 3-4 years ago. So as you can see, this is basically your GPU. GPU has multiple of these SMs. In this case, we have 16 of these. The L2 cache, which is the shared cache between SMs, usually is somewhere in between. There is private cache within this SMs. Okay. So this is your L1 cache is basically sitting here. And then your DRAMs is kind of distributed on the size of this system, okay? So your DRAMs is basically it's your global memory that is kind of like, you know, sits in between. And then we have controllers and so on in this system as well, okay? So multiple SMs, each SM has its own private memory, and then there is shared memory between SMs. If we zoom in into one of these SMs, that's what we get on the right side. So you will see that there is like an instruction cache. There is a whole bunch of schedulers and dispatch unit. Think about this as your rename and your dispatch unit, your reservation stations, and your decoding logic. Then you have a really, really big register file. So your register file, look at the number that you have. You have 32,000 of registers as opposed to 64 or 128. And then you have a whole bunch of cores here. And these cores, if you count them, it's typically 32. Okay. And these cores, think about it as basically, so this is like the zoom in version of the cores. Cores are basically an advanced version of a functional unit. It's not just a functional unit. So actually, this is the functional unit. It also has, you know, think about it as some form of a reservation station. It's kind of like our reservation station is divided into half. Part of it is here, and part of it is here. Because we need to read lots of register files, so reading register file is a little bit challenging in GPUs. So that's why you need to what we call an operand collector to kind of go and read things from the register file, do the forwarding and masking and all those things, okay? So the way this works is we're gonna have a big grid. The grids will be divided into blocks. Each block gonna be, assigned to these different SMs. Within each block, we have lots of threads, right? So we're gonna schedule those threads in 32 numbers, and this is called one warp. These warps will be then assigned to these 32 different cores, and the core is gonna run this and create the results, and then we're gonna get the results back. As you can see, there is functional units and there is load store units. So similar to the way that we kind of distinguish between our regular ALUs and our load and stores, we have the same thing here. So if you want to read and write things, we assign it to our load and store. And there's also special function units that do some special activities such as sine or cosine. If there is a specific instruction that requires more work than just addition or multiplication, typically goes into this special functional units, okay? And then as you can see, there is an L1 cache that is kind of talk to these cores if need be. So the cores are private to each SM, but as I told you, there's a level 2 that is shared among all these SMs, okay? And then there is a DRAM that's kind of scattered around, and this is the global memory that everybody accesses. Same way as CPUs, accessing L1 cache is much more faster because the connection from here to here is very small. Accessing L2 is a little bit, slower, and accessing to DRAM is really slow. Okay, so same way that you want to have a good cache hierarchy strategy, you want to have the same thing on GPUs as well. Okay, any questions? So this is again kind of combining the block ID, thread ID, and the functional units together. So think about a GPU as a many core system. So instead of having 1 or 2 cores or 8 cores that we have in CPUs, we are talking about thousands of cores in a GPU. So as I told you, we have threads. This one is the thread. This box, a group of threads, we call a block thread or thread block or TB. And then group of thread blocks will be a grid, okay? The grid could be 1D, could be 2D, or could be 3D, okay? And then we're gonna assign each of these blocks into SMs, right? So each one of these is assigned to one SM. And then we're gonna assign all these threads into this functional units here. And then we're gonna write the results into the devices. And then if you have multiple of these SMs, we can run multiple of these blocks in our different SMs. Okay, this is how we get the parallelization that we want. All right. One big question is that can you have control flows and things like that on GPUs? And the answer to that is yes. The problem is that since we are doing single instruction, multiple data, we cannot have separate instructions for separate SMs. I cannot run one thing here and another thing here. I can only run things at the same time. And as a result, we're going to have what we call a branch divergence. All right. So if you think about that, okay, these are all the threads that I have. And let's say these are 32 of them. If there is no branch divergence, all of them should execute same instructions all the time, right? So we're going to just assign 32 of them to 32 cores, and then we're going to move on, and that's the best performance that we can get. There will be a point that there's going to be if something, do this, else do that, right? And this if the condition here is based on the data. So for example, it says if x is less than 0, do this. If x is bigger than greater than 0, do that, okay? So in that case, it's data dependent. Some of these threads would be a negative number. Some of them might be a positive number. So in that case, some of them needs to execute these instructions. Some of them needs to execute these instructions. And that's why we call this a branch divergence, which means that we're going to divide this group of threads into 2 groups. We're going to run the first group first. These are, for example, those that are the the taken branches. And then we're going to run the second group, which is the, the complementary group of those other threads into the else branch. So, so we kind of like, runs a few of them. We're not going to utilize the entire SM. We're just going to utilize partially the SM. And then we're going to run this for the else. And at some points, they're going to reconverge because at some points, both the if and else finishes, and then we're going to continue the program. Okay. And this branch divergence is a big challenge in GPU systems because obviously it means that we cannot have the maximum parallelization that we want, right? And in order to fix that, we need to either, remove the branches altogether, or there are a whole bunch of, research on how do we do this, proper scheduling and so on and so forth. But keep in mind that you can have branches and you can have control flow, but what will happen with your control flow is that you're going to have divergence. All right? Any questions? And this is kind of one example of how a CUDA program looks like. So this is for example, if you have a program that's kind of like, a for loop that do, addition and multiplication in C, if you want to create the CUDA version of this, what you will need to create is you need to create your thread blocks and thread IDs. So for example, this is the number of your block dimensions, in this case 256, and the number of blocks is basically depends on what's the size of this n is. So if n is, for example, 1024, you need 4 blocks, right? If it's bigger than that, you need that, right? So basically what it says is I need to divide it by 256 to get the number of blocks that I need, and that creates my grid. Then what I would do is basically I'm going to rewrite this program, and keep in mind about this, keywords. So this host means that this part will be running on the CPU, on the host machine, and the device means that this part will be run on the GPU. Okay. So on the GPU side, all we need to do is basically using this index and this block ID, then run this application. So all it says is that if your thread ID is 00, for example, you need to get X0, Y0. If your thread ID is 1, you need to get X0, X1, Y0, and so on and so forth. All right. So basically, this thread ID will tell you which number you are assigned to, and then you're going to do the instruction. And remember, we are talking about SIMD instruction, which means that all this data are going to use the exact same instructions. All of them will go through this multiplication here, then addition, and then assignments to this, right? So basically, this would be the program that you're going to write. Again, if you want to learn more about CUDA programming, you have to take another course and learn more about this. But the general idea is that there will be a host part, which is the CPU part. There will be a GPU part or device part, and you have to kind of like write all of them in the same single program, compile it, run it on the actual CPU. The CPU will understand what to do, and it will offload that kernel, which in this case, this is your kernel, to the GPU. The GPU will follow the thread ID, block ID in order to understand which thread is which. The scheduler is going to schedule those threads for you. You're going to get the results back once it's finished, and then you move on to the next part of your program. Okay, so that's kind of like the life cycle of your GPU system. So what are the challenges? I told you about branch divergence is a big problem. The scheduling of threads is another big problem. Like if you have multiple blocks and we have multiple grids, how do we schedule this to get the best performance out of the system? The design of the register file and reading from the register file is a big challenge because we're talking about thousands of registers in, compared to like, few hundred. The memory design, how do we do the caching? How do we design the L1? How do we design L2? What is the bandwidth that we need? And so all those things is another big problem. And then the power of GPU is also another big challenge because we are doing lots of things at the same time. So there will be lots of power consume in the GPU systems. Okay. Many of these challenges are actually shared with CPUs. We talked about a bunch of them actually in the course, but some of them are particularly more challenging in GPUs because we're talking about much more mass scale system in GPUs. Okay. Any questions about GPUs? All right. Let's have a quick break, and then we're going to talk about the accelerators a little bit too. Any questions? So another thing that I want to talk about is about specialized hardware. Remember, I told you that, at some point we decided that, okay, just building a data path and controller that is good for specific ISA is not enough. By the way, can you write down your names? I just want to make sure that I have names of people in the class for your participations. Yeah, it's going to be campus wire plus participation. So, I mean, you won't lose points if you don't participate, but you get more points if you participate. So that's why. Anyway, so specialized hardware is going to be used for cases that we're going to create a piece of hardware that is specifically designed for one class of applications. Okay, so the CPU still is the interface, but the same way that we did it for GPU, we're going to offload things to our accelerator in order to run things fast. Okay, and GPU is kind of like one example of this idea. Okay, so it's not just GPU. We can actually accelerate many other things. Okay. So the GPU accelerator model would be something like this: that we will have our CPU. We will have our, caches and our memory hierarchy and so on and so forth, right? And then if you remember, we said we had this bus in I/O, and then we have a bunch of different I/O devices here, right? So some of these I/Os could be the accelerator, okay? So basically, the CPU is still, again, going to see a kernel. Instead of running the kernel on the CPU, it's just going to run things on this accelerator. All right, we typically call this a loosely coupled, but another alternative is instead of like having the accelerator as part of like an I/O component, what we can have alternatively is, I'm going to write it here. I'm going to have the CPU and I'm going to add the accelerator kind of as an extension to the CPU. Okay, so the difference between this one and this one is that then this accelerator has access to part of my CPU. For example, the accelerator might have access to my register file. The accelerator might have access to my reservation station or ROB and so on. So this is typically we call it the tightly coupled accelerator, which means that it's just part of the CPU itself. We are kind of like, it's as if that we are adding things to our data path in some sense. And then we can have a completely independent piece of silicon, a chip, that just sits into your I/O system, and then add that to our systems, to our portfolio of various different things that we can have, and then we can make our system faster that way. Okay. So we can have loosely coupled accelerators, we can have tightly coupled accelerators. Both of them are extensively used. And this one obviously is much, much more faster because it's very, very close to the CPU. But it means that it's kind of like, you need to add it with the CPU itself, versus this was completely independent. Okay, so this one is basically the idea of GPU. So GPU is also kind of sitting here. And as I told you in one of the lectures, this connection can be really, really fast. Okay, so we can have something like a LAN connection or so on, a PCI Express and so on. So this connection could be fast, but still it's outside our processors. Okay, so the question becomes what to accelerate. And I already talked to you about, told you about matrix multiplication. It's one of the biggest candidates. The reason that matrix multiplication is becoming really important these days is because it's extensively used in machine learning, particularly deep learning applications. And deep learning itself is really, really useful because it allows us to do group of, new challenges and problems that we couldn't do before. Right? But there's other things. There is encryption and decryption that usually done in accelerators. So most of these systems, including Intel processors, typically have their own accelerators for encryption and decryption. For hash functions, we use that. For convolutions and other signal processing applications we might have. And these days, there are many, many different accelerators depending on the need that can be added to your system. Okay? So how do you design an accelerator? So the accelerator design is fundamentally different than the way that we design our CPU systems. On CPU systems, as I told you, we are following the store program order, or in some sense, what we call a von Neumann architecture, which we're going to have instruction set architecture, we're going to have memory, and we're going to have CPUs, right? And basically, we're going to have a program counter that kind of goes through instructions one by one and execute that. That's the model that we use in our general purpose processors and in some sense in our GPUs. For accelerator, we typically go with the other approach, which we call a data flow approach. In a data flow approach, we are not using the program counter. We're not using instructions. We just follow the data flow of a program. So for example, if you need to add those two things and then multiply them, you just create an adder and add it with the multiplexer and then wire them together so that at the end the result is what you need. Think about it as a data path that we created in our system. Okay, so there is no program counter. And there is no control flow or different instructions. It's just data flow is basically based on the steps that you need in order to compute that function. If you need to add, then subtract, then XOR, then OR, whatever you need, you just do that. You create the elements for each of them. You might rewire things back and forth, but that basically would be it. So there won't be any controller to kind of orchestrate this for you. All right. And this way, we're going to have what we call a data flow architecture. And for accelerators, since we are only running one specific application, data flow is the way to go because it's much more faster and much more efficient. Okay. And that's kind of the design of an accelerator. Of course, you can have a von Neumann architecture for an accelerator too. But it's not common to do that because, again, you're only implementing one hardware. So you basically kind of hard code the controller and the steps in that system. Okay. So to give you an idea, let's say we have something like this. Okay. So let's say our A and B are the inputs, and we want to do a bunch of different things. Okay. So what we do is saying that, okay, this is my A, this is my B, and then I'm going to just add them together first. This is the first instruction. Then I'm going to multiply B. So this is B and this is A. I'm going to multiply B by 2, right? And then, so this is my W and this will be my V. And then I'm going to subtract V by W. So this would be a subtract. And then I'm going to add V and W, and this would be my X. And then I'm going to add V and W, and this would be my Y. Okay. So this is basically the data flow. My data flow is basically a bunch of adders and a bunch of multipliers and a bunch of wiring based on the functionality that I want. Okay. And I don't have any instruction set. I don't have any decoding. I don't have any fetching. All we need to implement is this wiring. So I need 2 adders, 1 subtractor, and 1 multiplier. And I just wire them together, and that's it. And I'm going to get my X and Y. As long as the correct B and correct A comes in, this is A, right? Then I'll get my correct X and Y. Does that make sense? Anybody has any questions? Okay. So to give you one example, there's very famous accelerators, kind of like, one of the first few accelerators for machine learning called Iris. And I'm gonna just briefly just talk about how Iris works, very, very briefly. So the Iris is basically, at a very high level, the Iris is an accelerator for machine learning for matrix multiplication. That what it does is basically it's loosely coupled. So think about this as one element that's kind of sits in the bus, and the bus is kind of like goes into the CPU. Okay. Within this accelerator, we have what we call a processing elements, or PEs. We can have 16 or 256 or whatever number of PEs. I'm just showing 4 here. This has some form of a buffer that I'm going to talk about, and then there is DRAM that's talk to the accelerator as well. We can have our internal memories here if you want to, and that basically what this buffer does. But they can also talk to my DRAM as well. They cannot talk to the cache, but they can talk to the DRAM as well. Okay. So let's see how this works. So what we want to do is doing a matrix multiplication. Matrix multiplication, as you know, is typically 2 inputs. There's one is filter and the other one is the input image, and the output is the matrix multiplication, the results of this multiplication. Okay, the filter for machine learning is typically what you train for your model, right? So your model will be a bunch of neurons, and each neuron typically is just one filter or a group of filters for different channels in your image. And what you need to do is that you take the input, you multiply this, add it, and then go to the next one, and next one, and next one, and that would be basically your neural network. Very simple, description of a neural network. Probably if you guys have taken any machine learning course, we'll learn more about that. But for now, we don't need to care about how a neural network works. And let's say that this is the problem that we want to solve, and Iris can solve this problem for us, okay? So for example, in order to do this multiplication, what we need to do is doing it row by row, right? So we take this row and take this row, multiply it, and that would be the results for this. And then, as you know, since the matrix multiplication is kind of like, a combination of multiple rows and columns, this is not the final results. This is the partial sum results, right? So it's just like, you multiply this with this, and then you multiply this with this, and so on and so forth. But at any given time, you're multiplying multiple things together. Okay? So how does this work? So let's say you have one row of your filter, one row of your image, and you're going to get to your partial sums. Iris, particularly what it does, it has 3 different buffers, okay? And then the buffers are actually, there are pipeline. So all it does is basically, multiply the image with the filter, and then keep doing this for all the inputs, right? So for example, if there are 3 of them, you just repeat this multiple times. So you have multiple, multiplications. And then you then add it with your partial sum, and then you get the results that you want, okay? And again, if you think about the way that, matrix multiplication works, is that you multiply 2 elements, add it with your partial sum, go to the next one, go to the next one, and so on and so forth. All right. So this is kind of the idea of how we design our data processor. And this is one processing element. We might have multiple of these processing elements, and each one doing the exact same thing, but for a different row. Okay. And since we have, for example, a 3 by 5 by 5 times a 3 by 3, then we can have a bunch of different processing elements at the same time. Okay. And it's kind of like, this is basically showing how we are kind of assigning different rows and different for different columns. And this is where we're going to get the final results. Row 1, 2, and 3 will be basically the final results of your system. Okay. Any questions about the accelerator? So to summarize, what you need to do is think, what is your problem that you want to solve? For example, in this case, it's a matrix multiplication. You take the rows, you take columns. So you need to design a piece of hardware that kind of like takes this, you create right buffers, you add pipeline registers, you add multipliers, you add adders, And if you follow this format, we'll see that it basically will be very similar to what we showed here, right? So just the functions and the activities kind of change, okay? So this basically becomes my processing elements, for example, in this case, okay? And I build a bunch of these processing elements depending on how many of these I want to run in parallel. And then I finally get my results by wiring and combination of these processing elements together. And this happens in parallel. And with just within one cycle, for example, we get the results that we want, okay? And that's kind of it for a matrix multiplication. That's as simple as that. You can have an accelerator for your matrix multiplication, okay? Any questions? All right. So kind of like, summarize the idea of an accelerator. So you need to first kind of come up with a design. You need to make decisions about, are we going to reuse some blocks, or are we going to use it for every single, flow? So for example, if I go back to the examples that I have, for example, I have an adder here and I have an adder here, right? So I have two adders. What could have done is basically, for example, from here, I could have add a register here and it's kind of move this back and reuse one adder, right? This is kind of a balance between can I do things in one cycle or whether I need to do it in multiple cycles. Remember, we had the same idea in our data path systems, right? We might have one adder and reuse that, or we might have multiple adders. So this is kind of one of the big decisions that you need to make. You need to also make a decision about how you're going to use your memory system, right? And how you're going to design your marker architecture. So all these different things, as in how do we do pipelining? How many stages do we need? What's the buffer size? What is the bandwidth of the memory? And all those things. What's the data type? What is the data size? Whether we're going to use 32 bits, 64 bits, and so on and so forth. So these are all the questions that when you're designing an accelerator, you have to think about what is the kind of a trade-off for each one of these. What is the problem that you're trying to solve? Is it a matrix multiplication? Is it encryption, decryption? Is it hash function? What is it? And how much you want to pay for it, right? In terms of hardware, in terms of power, in terms of performance, and so on. But at the end of the day, once you have finalized all those things, you're going to implement your hardware and you're going to get your accelerator. But the accelerator is much, much more faster than your regular CPU because it's designed to do these things in parallel within one cycle, right? Versus your CPU is designed to run one instruction at a time, okay? So every addition with one cycle, every multiplication one cycle. If you have multiple data, it takes one cycle for all of them. Versus this one can run things in parallel all at the same time, okay? And that's where you're going to get the performance boost that you want. There are also other examples of accelerators. You probably heard about Google TPUs. You probably heard about systolic arrays. There are many, many more accelerators compared to Iris. It's actually, past 5 to 7 years was the explosion of this accelerator designs in research communities. So there are many, many more of these different designs. Iris itself has version 2 and version 3 and version 4 and so on and so forth. So different applications, different needs, and also it's a trade-off between the power and the performance. So if you want to add more processing elements, you can, but it means that you're going to consume more power. Okay? Any questions? All right, so to summarize what I just said in this lecture, I wanted to give you kind of a perspective of the range of solutions that we use in hardware in order to run things faster. We talked about CPU, we talked about multi-core system as kind of next step for the CPU. And then in this lecture, I talked about domain-specific accelerators. We talked about GPUs, and we talked about specialized accelerator, for example, for machine learning applications for matrix multiplication. Within each family, we're going to have also different options, right? We can have in order versus out of order. We can have a really, really large accelerator versus a really, really small accelerator. So all of these things depends on what you're going to have and what you need in your systems. If you pay more, you're going to get a better system, okay? And these days, accelerators, GPUs, and CPUs are all standards in most modern systems. So your laptop, like your new Mac has a GPU, it has a neural network accelerators, it has accelerator for cryptography. We usually call it secure coprocessor or cryptography processor, and it has a bunch of different CPUs with different systems. So it usually has what we call a big and little cores. The little cores are those that are smaller and in order. So some of the applications are run in the little cores, and those that requires more power and more performance runs on the big cores. Okay, so that's kind of like the arsenal, the set of tools that we use these days in order to have the range of different things that balance between power and performance and systems in general. Okay. Any other questions? All right. So from now on, I want to talk a little bit about your quiz, and also I want to talk about just generally the things that we covered. Okay. So the topics that we covered, we start with the ISA and the hardware software interface. Then we move on to how we implement this ISA in hardware, and we talked about the microarchitecture. We talked about data path and controller. Then we start talking about lots of principles in order to make this system faster. We talked about pipelining, we talked about parallelism, we talked about speculation and prediction in general, right? Then we moved on to memory hierarchy. We talked about caches and memory hierarchy. We talked about various different things, including what we do for replacement policy, why we need multiple level of caches and so on. We talked about main memory. We talked about virtual addresses and all those things. Then we moved on to multi-threaded systems, and we particularly talk about, cache coherency problem, consistency problem, and today I talked about GPUs and accelerators, and I also talked about the whole SoC system, which has all these IOs and the way that the IO talk to each other and so on and so forth, right? If you look at all these things, you'll see that there are a bunch of ideas or tools that we use very often. And it's one of the things that I want you to remember from this course. So the first thing that I talked to you about was the use of abstraction in order to simplify this model. If you've seen, we talked about the CPU first and say that, oh, memory for us is just this black box that has things. Then later on, we go into the memory and say, oh, memory itself is lots of different things. It has TLB, it has a level 1 cache, level 2 cache, and so on and so forth. In all these different parts, we always say that hardware itself is an abstraction, right? So we don't know what is going on inside this adder. We just know that this is an adder. How it's actually implemented, you need to understand the logics of that, the transistor, how they interact with each other, and so on. But we use abstraction to simplify our understanding. And you keep using this for other things that you use in your systems. Generally for computing systems, this is very helpful. But in many other applications that are completely irrelevant from computer systems, using abstraction also is very, very helpful. Another thing that we do a lot when we are designing our processor was making the common case fast. If you remember, we said that when we are, for example, having a branch, let's guess and then just move forward. And if we make that guess correctly more than 50% of the time, we're going to get performance benefits because this becomes the common case. And if the common case is the fastest way of doing things, then we're going to get the performance benefit, okay? And if you look in your life, you will see that the common case fast strategy is actually used in many, many different systems as well. So it's not just about computer architecture, about processors. You will see that making the common case fast is actually used in many, many different systems as well. Parallelism is another one that we use a lot, right? So whenever we wanted to make things faster, we do parallelism, right? We added more lanes to our processors. We do 32 bits to 32 bits and then parallelize it to 64 bits to 64 bits. We then talked about, adding more cores to the system. So not only having multiple lanes within one core, we parallelize it even further and add more cores. And today I talked about, even further than that, you can have many different register files and you can have many different cores at the same time. So whenever we need to make things faster, parallelization is generally the way to go. But as I told you, Amdahl's law will limit your parallelization performance, right? Another thing that we used a lot was pipelining, right? So we basically, instead of doing one thing in one go, we said that, okay, let's do these things in smaller steps and then kind of overlapping things, right? So pipelining is another main idea that we use. And again, pipelining is something that we use a lot in our daily life too. Prediction and speculation in general was another idea that we used. We tried our best to make our prediction as accurate as possible, but the fact that we are basically using this technology that we are saying that, okay, we don't need to wait until things happen. We can predict and we can recover is also, is something that we use. So, you taking calculated risk in some sense is a good idea, and we also use it in our everyday lives. And then finally, the idea of hierarchy, right? So the idea of the hierarchy is for giving you this illusion that you are talking to the best one versus it's basically kind of like, trickle down all the way to the bigger memory, right? So the hierarchies, again, is one of the ideas that we use a lot in this course. And you will again see that this hierarchies is something that you will use in your day-to-day life as well. Okay, so this is kind of like it for your modern systems. This is basically a photo, die shot of a 4-core Intel processor, I think a few years ago. So you will see that this is basically your cores are kind of like, somewhere in between. Your caches is actually usually here. This is your L1 caches. Then you will have your L2 caches is kind of like sit in between cores. And then you have your DRAM interface that basically talks to your DRAM, and DRAM is basically off chip, right? So your DRAM is a separate unit that you buy and you put. DRAM itself has a bunch of different banks. So these black things are called banks. And then usually has 2 sides, which call DIMM. So if you actually look at your DRAM, you will see that you see 8 of these in one side, and then if you look at the other side, you will see another 8. So it's not the same thing. Usually we call this DIMM 0, and the other one is DIMM number 1 on the other side, and then there's banks. We didn't talk much about how do we actually access the DRAM, but the DRAMs is in DIMMs and then banks and then grows. Okay, so we basically go from here. We first select whether we're going to access this side or the flip side. Then we're going to select which of these banks we're going to go to, and then within that bank we're going to go to a specific row. Okay, so that's the way that we're going to access our DRAM. And this is basically our shared L3 cache, which is really, really large and it's far from cores. A big thing to remember is that the distance also matters. So for example, if you want to access something from here for core 0, it's much, much more faster than accessing the same thing from core 1. So placement of things in our L3 and L2 is also matters. And that's one of the key things that people do in order to make their systems more efficient. Okay? Any questions? This is another example of a modern systems. This is your M1 chip. As you can see, it has 4 high-performance cores. These are your high-performance cores. It has larger instruction cache. It has a shared L2 cache. These are smaller cores, which Apple calls it high-efficiency cores. The difference is that it's smaller in size of the execution. So it's, as you can see, it's called ultra wide and wide. My guess that this means that it's probably 32 and this means probably 64.
The instruction cache and data cache is much more smaller, as you can see. And the L2 cache for these are also smaller, okay? The reason that, typically these systems use multiple different cores is that these cores have better performance, but they are also much more power hungry, right? Because they're using 64 and so on. These are more efficient in terms of power, but they have lower performance. So the operating system actually intelligently, map different applications in different systems. So for example, if your system is in sleep and all you need to do is, for example, unlock your phone, you probably want to use your high efficiency cores. You want to shut these down to avoid, leaking power and leaking energy. And then once you, for example, start, your browser or start gaming, then that task will be assigned to this high efficiency, high performance cores, because they will use more energy. Okay, and then this is the entire SoC. If you remember, I told you about more than more and said that basically these days people can actually put more things into the same chip. So this fabric is basically that bus that we talked about in the class. You see that there is CPU, there is cache, there is neural engine, there's GPU. And then you see that their memory is actually also part of the same silicon. So unlike the previous one, that this is like really, really slow bus, this one is really, really fast because they're part of the same silicon chip. And that's where they're going to get a lot of performance. That's how they can beat Intel and AMD in terms of performance, because the communication between the memory and CPU is really, really fast. Okay, so that's another thing to remember. And as you can see, your GPU and your neural engine is also connected to this fabric. So that's why they can actually offload things to their GPU also quite fast. Okay. These are other examples of like smaller systems. This is an ARM processor. This one is a TI processor that I show you. You see lots of different IOs in this systems, right? So bunch of different things. This is a different paradigm, right? You need lots of, communication and IOs versus, on the Mac, you probably just need a CPU and GPU, okay? So different paradigms, different things you need to add to your system, but hopefully you can understand all these things. So even in the mobile system, you see that there is a core, but also there is a GPU, and these are a whole bunch of different accelerators. So for example, this is a codec accelerator. This is an LCD video interface, which does particular things. And this is your interconnect, your bus, and then you see there are lots of different things. There's an audio, there's DMA, SD card, bunch of different connections such as UART or SPI or JTAG and so on and so forth. Okay, so the idea is basically they're connected, and each of these are connected to like other modules. So for example, you have a Bluetooth module itself, it has a core in itself, right? So this one is like a Core A9, right? So Core A9 is like a high performance core, versus this M series is more of like an efficient core, smaller cores. They're in order. They're much more power efficient. So each of these units, your Wi-Fi module, your Bluetooth module, your 4G module, and so on and so forth, each one has their own core as well. Okay, all of them following the same principle, but just different functionalities and different requirements. Okay. Any questions? All right, so the last thing I want to talk about before you leave, it's, often what happens is that you take a course, you learn lots of things about it, take the quiz, and that's it, right? So, and then if you look back 1 year or 2 years from now, yeah, there will be a very tiny amount of things that you will remember from the course, right? So what I want you here is to kind of like, just give you some guidelines of what you probably want to remember from this course. I want you to remember that generally the way that the hardware and software works is through some things called an ISA, okay? So there is a, set of, a contract between the hardware and software that both of them agrees in order to follow, okay? And we call that ISA. It's RISC-V, x86, and so on. You won't remember what was the opcode or what was RS1 and RS2 and so on, and that's totally fine. But just know the concept of the ISA, And also remember the concept of how we implement this ISA through the microarchitecture. Like what was the thought process of that? Again, you won't remember what we did for the register file or what we did for the image, immediate generators and so on. But remember that, oh, we had this different opcodes and RS1 and RS2 and so on. And we needed to implement this using a data path controller. How we did it, I don't remember, but we kind of like follow specific steps in order to do that. Okay, so remember that. Remember the concept of generally the control path and data path. Remember the fact that we added pipelining in order to improve our systems. And also remember the out of order execution and the reason that we need out of order execution. You probably won't remember what was ROB or reservation station and how did we did the renaming and so on. But remember that we kind of like, read things in order and then execute things out of order. And that gives us lots of performance benefits, okay? Another thing that I want you to remember is that the concept of speculation and prediction, okay? That in many, many cases, since we didn't want to wait for the system to kind of resolve an issue, we just make some guess, we make, forward and we continue our execution and then we come back and fix it if we needed to, all right? And then also remember about memory hierarchy in general. There is a cache, there is a memory. It matters how you actually access this cache. It matters how you orchestrate this data movement and so on. You won't remember the details of that, but remember that it matters and you have to, follow the specific format in order to do that. Also remember and think about virtual memory, because that's also very important. The fact that we have virtual memory for our processes, but there is also a physical memory that kind of like, interact this. That would be useful in future for you guys as well. And finally, like, the idea of how we write parallel programs and what are the challenges in parallel programs is important things to remember, especially if you made a career into like, systems that deal with parallel programs, you will come back to these concepts a lot. So have an idea of what is coherency problem in general and what is a consistency problem in general will help you in future to remember these things. I typically put the slides and videos available online. So feel free to reach back, go back to them in future. Hopefully we'll be there. I've get, comment and requests for people accessing CampusWire as well. Typically we have it available as long as CampusWire is there, but my guess is YouTube is probably will be there, and my website is, since I'm managing it myself, hopefully will be there. So you can always go back to those little videos and watch them if you want to, okay? Yeah, and then finally, these tricks that we use, right? Things like optimizing for a common case, and speculation, hierarchy, pipelining, parallelization. Remember these things because you're going to use it not only in this course, but also you're going to use it a lot in your other similar problems, right? So you never know. You're going to write this piece of software or work with another system, and sometimes you're going to use this as a good tool. And this is a tools that are not just computer architects didn't come up with this. This actually the tools that was there before, and we just apply it to our computer architecture problems. So the same thing can happen for other things in your life. And finally, I want you to, the same format that you come into the class without any information about computer architecture, you listen to the logic, you use your own thinking in order to understand things. Apply this to the rest of your life too, okay? So there are many things that, we come out of this class and say, okay, now I know everything and I can make comments about many different things that I have no idea about. I can comment about, economics and politics and medical and all those things without any knowledge. The same way that you don't comment about caches because you have no idea, please don't make comments about other things that you don't have any idea, right? Go and listen to the experts on those domains, learn from them. Once you have the feeling that you know those things, then make a decision about those things, okay? So use logic in your life because that's the way to go, okay? Learn from the experts in that domain, whatever that domain is, and use that knowledge in order to make your decisions, okay? So let's that to be a lesson for me to you, okay? One more last thing I want to talk about. We talked about we didn't talk about many other things. Generally, this course is very packed, and the reason that I did this way was given that for many of you this is the only time you're gonna interact with hardware. I wanted to talk about many different things. In many different courses, you won't see, for example, out of order execution or coherency or consistency. What I wanted to talk about them, that means that we sacrificed a little bit of depth in some of these topics, but that was intentional. And we also didn't talk about some other topics that you might see in other similar courses. We didn't talk about VLIW. We didn't talk much about the storage systems. We didn't talk about vector systems and server systems. We didn't talk much about power. We talked a little bit about compiler and the operating system. And I definitely recommend you that if you're into these topics, go and take a course in operating system. And we talked a little bit about security, but if you want to learn more, I'm actually offering a course on security, okay? This is a really good video about computer architecture. It's actually done by David Patterson and John Hennessy, which is the author of the book that you read. They won the Turing Award in 2017, and this is the talk that they gave for acceptance of that award. Turing Award, for those of you who don't know, it's kind of like equivalent of Nobel Prize for computer science. Okay, so if you win this, it's a huge deal, and they won it jointly mainly because of their contribution to computer architecture. And yeah, it's a 1 hour video. Whenever you get the time, just watch it. It's a nice thing to look at. It's kind of also kind of go through these things that I talk about during this course, and you will see lots of figures and terminology very similar to what we said, because we kind of like use their slides and their book in this course. Okay. If you want to follow me, you can follow me on Twitter, on LinkedIn. If you want to see more cat photos, we have an Instagram page for my cats. You can follow that. I have my personal page and my website for the lab. If you want to follow our research, you can go and follow us there too. Okay, and keep in touch. We always want to be in touch with all the students. Okay, so if you have any questions or requests, feel free to email me. Okay. Don't forget about the evaluations, right? The evaluation is due on Saturday, and then we're gonna add 5 more points if you have 75% participation to your quiz 3. If you really do well, which we haven't done so far, we're gonna add 88% to your quiz 3 if you have 90% plus participation. Okay. Last time I checked, it was yesterday, it was 25%. Hopefully today is higher. Okay. And your evaluation, please talk about things that you liked about the course and the parts that you didn't like about the course. As you know, the feedbacks are completely anonymous, so feel free to and have any kind of like critics that you have, things that you didn't like. Talk about different components of the course, like did you like the lectures? What needs to be changed in the lectures? What about the homeworks? What about the projects? So talk about each one individually, and I read them very carefully, and I actually change the course based on those reviews. Okay, so the past 2 versions are slightly different than this version, mainly because the feedback I received the first time and the second time. So I'm going to read this and I'm going to use it for next year. That I'm going to teach this again. So it's actually, you have a very high impact on changing things in your courses. If there are parts that you didn't like, put it there, and I'm going to read it and I'm going to change it if the majority of you actually think that this is problematic and so on. Okay. And finally, your quiz 3 is going to be anything that we discuss after quiz 2. So it's going to be virtual address and virtual memory. It's going to be a little bit of about I/O and all those things. Then it's going to be about cache coherency and memory consistency. Probably we're going to have 3 different questions. One about memory consistency, something similar to your homework. So we're going to give you a piece of program, and we're going to ask you what are the outputs of this, or change this to create this output for us. Very similar to what you've seen in the homework. Make sure that you understand the difference between a log, a fence, and generally barriers and synchronization. Also make sure that you understand the difference between a TSO and sequential consistency. One thing that I see often people make mistake is the fact that we have also raw data hazards and dependency within a system itself, within a core itself. When we are talking about memory model, doesn't mean that now we can just reorder everything. No, still we need to follow the program order. There is still dependency between instructions. There's still dependency between values. Adding more cores doesn't, ruin that. Okay, so still we have all those things. So don't think that, oh, I can just move everything around and there could be any possibility. No, it's not like that. Still have your hazard detection units, you still have your forwarding and all those things. Okay, and it's only that, when you have independent values between the cores, different cores might see different things. Okay, so that's the entire problem of synchronization. So the synchronization doesn't add new problems. It's just the way that the system works is like that. Okay, so when you're sort of solving the homework problem and solving the quiz problem, just remember that still you have to figure out the raw data hazards and so on. So one question about that. The second question probably will be about coherency. We're going to give you a sequence of accesses, reads and writes from different cores. We probably give you a MOESI or MESIF, something like that, and ask you to just fill the memory, very similar to your homework question. And probably the third question would be something around virtual addresses and maybe computation of that, or maybe we give you some small questions of like, what if we do this or that? Why are we doing this or that? Like short answer questions that you need to talk about. Why, for example, we have interrupts, not polling, or what's the difference between interrupt and polling and so on. So these type of questions are probably like, few of them in one big question. Okay, so that would be probably your quiz, question 3. Any questions? All right, that's it, guys.